Can you able to see my screen?
Yes, ma'am.
Okay, thank you. So I think I am audible now. So
Yes, ma'am.
okay. So in the last class, we have seen some shared memory and synchronization and all. So today we'll move on to what about L1 cache and shared. Okay. So here in this L1 cache, okay, we can do perform sharing. So here we are having one function that is CUDA device set cache configuration. So you can give the kernel name and what are the parameters required as an arguments. So this particular function has to be given on CPU. Okay. So here kernel name means the name of your kernel. Parameter means CUDA function cache prefer none and L1 comma shared. Okay, these are the parameters. So you can give in the parameters section. Okay. So here the 3.x means the CUDA 3.x version. So onwards, you can configure 32 KB for L1 and 32 KB for shared. Okay, totally 64 KB is available. So in that 64 KB, you can allocate 32 KB for shared one, and you can give the what about the size of the cache and what that is L1 and size of the shared here in the shared. Okay, so here you can achieve with the help of CUDA function catch prefer equal. Okay, these are all the function required. So already in the last class we have seen you can allocate space for L1 cache and you can allocate space for shared memory. So here the L1 cache and shared memory everything is available in a block. Okay, GPU block. So either you can give 32 KB, 30 plus 32 KB or 16 KB likewise. So you can change according to our need. Okay. So you can see here. So the kernel program is given and you're having one variable, shared variable data. It's an array. And after that, we are using some threads in that particular block. Okay. In the main function only, you are going to give CUDA function set catch conf. Okay. So this function will be given in the main function. Okay. So here you have to call the kernel function or you have to pass the kernel function as the first argument. So after that, CUDA function catch prefer L1 is given. Okay. So you can launch the kernel and you can see uh, here that allocation may be given. Okay. So other configurations are CUDA function catch prefer none. So here no preferences for shared memory or L1. So this is a default one. Okay. And here the CUDA function catch prefer L1. So that means prefer large L1 cache and smaller shared memory. Automatically, it will allocate some more space for cache and smaller space for shared memory. Likewise, also you can give. So otherwise, you can give CUDA function cache prefer shared. Prefer share, here what happens is large shared memory and small L1 cache. Okay. So the opposite thing you need is CUDA function cache prefer L1. So you will get L1 cache, larger L1 cache and smaller shared memory. So likewise you can give. So this is mainly for allocating cache and shared memory. Okay, so within a block. Okay, so while doing program, if you are having some data and if you are going to store it in L1 or your shared memory, so because uh, if more than one threads you are going to use means you have to use some shared memory. Okay, or some like var threads. In var threads you have to use around 32 threads. Okay, so that time you can store the data in shared memory. That so the program will be executed very fast because it is available. Data is available nearer to the threads. Okay. So either you can allocate some shared memory for some amount of time. We can say it is a static memory allocation. Otherwise, we can uh, uh, allocate dynamic shared memory. Okay. So when we can allocate dynamic shared memory is, so if you are not able to know the amount of shared memory required, so which is not unknown during the compile time while compiling the program, so you don't know how much memory is needed. That time you can use dynamic shared memory. Okay. And so this dynamicity you can specify as a third parameter of while launching the kernel. Okay, so while launching the kernel, you specify whether you need some dynamic memory or fixed memory. So in this previous case, throughout the execution of the time, that is the allocation of L1 and shared memory is fixed. Okay, that is static. While during that program compilation. Okay, so it may varied while doing dynamic shared memory. Okay, you can see the dynamic shared memory here. See here. So during the kernel launch, what you will do is will be given number of blocks and number of threads. Here. So size of the memory required for while compile during compilation is given here. Just a minute. Let me change the runtime. Okay. T4, no problem. Okay, so here we have to change this. Scanf is there? Okay, that's good. Then we'll execute. N. See what happens. So my internet is a little bit slow. Takes some more time. So I have pasted the program in chat box. Okay. See. Okay, if anyone is willing to execute and execute it and the result. So it's not coming. Okay. So here in this particular program, see here we are having one kernel program. So the dyn shared. So here one external variable is declared, that is a shared variable. Okay, so inside our kernel program. Okay, so next for this is an array. For this array, we are assigning the thread indexes and we are synchronizing all the threads there. Okay, so if the thread ID is even, then we are printing something. Okay, there in that particular array location. Okay, see here the main function. What we are doing is we are having 1 comma n, so nothing is passed here. Okay, so I don't know what happened here. And here we are allocating memory space dynamically based on the number of indexes in that particular array. Okay, so if the number of indexes is increasing, so based on that we are allocating memory space dynamically in the GPU. Okay, so next CUDA device synchronize has been given to synchronize the CPU and GPU, then it will be printed the returning to the main function known as executor. Okay.
Execute.
Okay. So next one is shared memory with multiple arrays. Okay. So we are using more than one array. So in this context, what we are going to do is the same thing. We are having one S external variable, that is a shared variable, and it's an array. Then we are having S1 and S2. S1 equal to S and S2 equal to S plus N1. So these two values are passed here. So int SZ and int N1. Okay. So after that, some calculations. Okay, thread IDX is less than n1, we are assigning that value to this s1 array. Other way is we are assigning some other value to the s2 array. Okay, so both arrays have some values. Next, we are synchronizing the threads. So after that, we are checking some condition. After that, we are printing the value there in the s1. Okay, so here what happens is the int s is set, okay, into size of int, okay, s is set into size of int. So after that we are passing the values, okay, s is set comma s is set divided by 2, that is n1, okay, that is passed here. So one block and 1024 threads have been given, okay. So likewise it is given that. Okay. So likewise, you can share memory with multiple arrays too. Okay. So either single array or multiple array. So you can what you can do is you can allocate memory dynamically on GPU. Okay. So next is bank conflicts. Okay. So here in shared memory is organized into 32 banks. So why? So anyone can give the answer in chat box. You know what is memory banks and all. No idea? Okay, so what is bank conflicts is if more than one thread is accessing the same bank. Okay, so that time we can say this is a bank conflicts. So usually while using the shared memory, we have to use the var threads. So that is a set of 32 threads. So all the 32 threads has to be shared the same memory location. And see here, access to the same bank or sequential. Okay. So most commonly it will be accessing the some sequential. Okay. Uh, so when there is no conflict, bank conflict is, so if between threads in different vars, okay, different set of vars, there is no bank conflicts. And between shared memory accesses arising from different instructions, okay. So if same instruction is accessing the same memory, that time different banks are accessed, that time you will be getting the conflict. Otherwise you won't get some conflicts. And so here the consecutive words are stored in adjacent banks. Okay, so nearby banks, the consecutive is stored. Sorry. And so if the consecutive words are stored in adjacent banks, already we can see that that is co-least access. Okay, so nearby memory locations are accessed. So it is a co-least access. It is again useful one. And sometimes the warp accesses to the same word are not sequential. Sometimes it may be sequential. Okay, so most of the time it's sequential, otherwise it may not be sequential. Okay, so here we are having 1000 s, size of s is 1024. Okay, some values are said here. Okay, 1 into thread IDX, equal to thread IDX. Okay. So here there is no bank conflict here. So we'll be having only one. Okay. If you are having 32, then some bank conflict will be there. You see here, if there is no bank conflict, see here, there is the banks are there are we are having threads 0 to 31. Okay. So 32 threads are in the var threads, and the banks are 0 to 31. Okay, that is 32 banks. Thread 0 is accessing bank 0. Likewise, it goes on. This is a sequential access. See here, thread 0 is accessing bank 0. Also, some other thread 16 is accessing bank 0. That time bank conflict will occur. Okay. And here, so there is no sequential access. So on each and every block is accessed by only one thread. So there is no bank conflict. Okay, if a block is accessed by more than one thread, bank conflict will occur, otherwise no conflict. Okay. Hope you will understood what is bank conflict and all. And okay. So here in this particular case, okay, so all the 16, that is 0 to 16 threads needed the same data in one bank. Okay, so here also some more set of threads needed data from another one bank. It is not a bank conflict. Okay, and here also some set of threads needed one data. Okay, so it is not a bank conflict. And here, okay, each and every one is accessing the same one. So based on your program requirement, you specify that. So already we have seen texture memory. Okay, so how we can define the texture memory, that we can see here. And texture memory is mainly used for storing streaming data. Okay, and it's a very fast read-only memory. We can read the data we couldn't store, and it is very much used for 2D spatial accesses. That is optimized 2D spatial access. We can go with texture memory. So how we can define is texture less than float. That is angle bracket float comma 2 comma CUDA read mode element type. Okay, TX. This is mainly for using for uh, texture memory definition. Otherwise, in main, what you can do is CUDA bind texture to array. You can convert that texture data into array data using CU array. And in kernel, you can convert it into a 2D spatial access. Okay. So these are the things you can use for accessing the data in the texture memory. Okay. See here, one kernel program is given here. So int width, int height, float theta. So all those values have been passed through the kernel. So we are calculating the x and y values, p, u, v values, and tu, tv values. Okay. So after that, so you are having one array, output array. So there you are converting everything into 2D. Okay. So that is converted into 2D, then it is stored there. Okay. So from the main program, we can access those data with the help of CU array. Okay. This is an example for your texture memory. So next is the constant memory. So while seeing the memory model, we have seen all those things. The one is all that is the L1 is accessed by all the threads in the same block. Okay. So and L2 cache is accessed by different blocks. Okay. So and the global memory, texture memory, and the constant memory is accessed by that is global to all. That means you can access by the grid. Okay. Grid contains block, block contains your threads. So here we are having the constant memory. The constant memory is again a read-only memory. For every streaming multiprocessor, you are having 64 KB. Already we have seen this one. 64 KB constant memory is available in streaming multiprocessor. So already we have used something constant there in some program. Okay, you can assign in this way. And some other memory copy statement is available, that is CUDA memcopy to symbol meta h meta 1 into size of unassigned, because we are having only one data meta of 1. Okay, so 1 into size of unassigned. Okay, this is the size of the constant data. Okay, so likewise you can allocate memory space in GPU. Okay, so in kernel, what we have written is the data of thread IDX equal to meta of 0. Okay, so what is there in meta of 0? That will be stored in data of thread IDX dot x. Okay, so this is the definition. You can write it globally, and in main function. So you can allocate in this way. Okay, allocate the same constant variable this way. After that, kernel things you want, you write. No problem. See here, this is a program. Constant memory, same thing. Same. This is available in the previous slide. Okay. So then we have written one another one kernel for printing that particular value. What is there in the thread ADX? And what is there in the data of thread IDX. Okay, so that will be printed with the help of another one kernel function. Then another one unassigned variable is used there in the main function, allocating the space there in GPU. Then this for CPU. CUDA MLOC is for, again for GPU. And so next, first kernel is called 1 comma 32. That is again second kernel is called using 32 threads. Okay, so the data is passed here again. Here also the data is passed here, and so it's returning the values. Whether it is executed or not, I don't know. It to be executed. Remote. I'll try this one, whether it is executing or not. I want to know. See. This one. This for constant memory. Yeah. I think there is some problem in this program. That's why it's not executing anything. I'll assign some values. Not executing. So here H-meta is given as 10, and and again one more variable, that is for GPU and size of NZ. Okay. So next is again we are having another one variable data. So for the data, we are allocating space in GPU, that is using CUDA MLOC. Okay, 32 into size of an ascent, because we are using 32 threads. Okay, I executed 32 threads. I have stopped it. So I'll execute it and then show the output. Okay, so before uploading notebook, I'll correct it. And so for that 32 threads, it's again having allocating the 32 spaces. Okay, so then calling it with the data. You are getting the results. Okay, just simply assigning uh, the thread indexes. That's all. So it's a constant memory. Okay, so here something which is general to that is, and you are having the version number of CUDA, that is 6.2 or 11.1 or 10 point something. So likewise it goes on. Nowadays we are having CUDA 12. Okay, so the number is major plus major dot minor. Okay, so it shows what are the features which are supported by the GPU hardware, and you can use this version number along with the application at runtime. Okay, what is the number of SM and all likewise. And CUDA version, we can say 10.1 and all. So here the compute capability. So we have in Tesla, Fermi, Kepler, Maxwell, Pascal, Volta, Turing, Ampere. So the latest one is Hopper. See here the compute capability of different versions of CUDA. So in 2.x and all, you are having the atomics in the float, watt, volt, sync threads. That's all. In 3.0, unified memory is available. You know what is the unified memory? The same memory which is accessed by both CPU and GPU. And 3.5, 3.7, 5.0, 5.5, they are having dynamic parallelism. And 6.x, you are having atomics double. And 7.x, we are having tensor core. And 8.0, we are having hardware asynchronous copy. Okay, asynchronization is also there in 8.0. Okay. So that is compute unified device architecture. So it contains both hardware and software, but nowadays it is known as the CUDA API. And you can write program C, C++, Fortran, OpenCL, and some other languages, even Python too. and all the remaining things. So already we have seen all those things. So the programmer, otherwise the compiler, they can organize the threads in thread blocks and grids or thread blocks, grids of thread blocks. Okay, and so kernel program on parallel thread blocks. Each thread within the thread block execute instance of the kernel and has the thread ID within its thread block. So program counter, register, per thread private memory, input and output results, everything is available. So all these things. Um, so the each and every thread has in its own memory. Okay. So we can say that is the registers, the help of registers, and also each thread block has a per block shared memory. Already we have seen all those things. Okay, we have a shared memory, how it can be shared, how L1 is used and shared memory is used, everything. Well, that is L1 is cache. And inter-thread communication, data sharing and result sharing in parallel algorithms. All those things are there. We'll see some more things about the atomic functions, and that atomic functions and the more than one function is combinedly executed there in the atomic functions. So usually read, modify, write in the same memory location. Okay, and atomic add. So actually, if any operation is performed as atomic, no other thread cannot interference that particular atomic threads. Okay, so that is the main thing, and the here what happens is if any thread has accessed some words in the memory using atomic operation, okay, and other threads couldn't access that particular memory location. So this is a concept. One memory location is accessed by some threads using atomic function means, so that location couldn't be accessed by some other threads. Okay. So already we have seen what are the atomic functions. Here we are going to see how we can use it there in the functions. Okay. See here. You can use atomic add address int value, int address unsigned int value, unsigned long in atomic add. Likewise, also you can use. Okay, here also same thing. For float and all, you can use. Okay, you know the explanation. So I'll move on to the next one. Atomic sub. Okay, for subtraction. So here unsigned int address and unsigned int value. Okay, that is subtracted from old value. Okay, so the new int value is subtracted from old value and the result is again stored there in the address of old value. Okay, so here exch you can use in this way. So int value long you can use, float also you can use. So next is atomic min, that is minimum value, atomic max for maximum value, atomic increment. Okay, so there is some program is available. I didn't open the program now. This is asynchronous. We'll see later. Clock. Okay, so see here one lock variable is used. Okay, and one variable is used in the device. So after that, we are having one kernel function. So next, that is compare and swap. That is CAS. And the lock variable is passed and 0, comma 1. Print of block percentage and thread percentage is executing in kernel section block adx.x and thread adx dot. Okay, so in which block and which thread it is executed, that is seen, and I don't know whether it is executing or not. And so this is for lock initialization. Okay, and does let's see. It is printed. Okay, two comma one. Only 32 is, so always thread 0 is executing. Okay. We are seeing blocks, we are having threads. So which thread is executing in the critical section? So that will be printed here. Okay. So fine. This code is fine. There's no need to save this. So there is another one program for atomic increment. Let's see what happens while using this. And the bank program is also there. Okay, so n is given some value, some two variables. You can use both it there in the list. Okay, if you have declared with the help of or start with the help of device, you can use it there in kernel and the CPU programs. And this is a kernel program. Again, we are calculating the ID. So here, work list of atomic increment of WL size. So the work list is your array. So in that array, we are assigning the value. That is atomic increment. So incrementing, then storing the same location. Incrementing, same storing the same location. Okay. So in that particular location, it take the value, increment, and store there. Okay. So our next kernel is a number of elements added. That will be printed in the next kernel. Okay. And so here atomic variable is initialized and the kernel 1 is called and the kernel 2 is called. Okay. So number of elements added is 256. Okay. What is there in the WL list that will be printed there. Okay. Okay, we'll see this bank program. After that, we'll move to the presentation. There is an unassigned shared variable, array variable. Okay, thread id is stored, and next is again one more kernel, and same size. Okay, it is multiplied with 32. So here, okay, so both are local variables there in the kernel, and the first one is called. After that, the time is calculated. Next, bank check. That is called some 1,000 times. Next, the clock is calculated. Again, the second kernel is called. Okay. So whether the bank is traded, what is the start time, end time, everything will be printed here. Yeah, I have to include some other file. I didn't copy that. Okay. Try this one. Okay, we'll see this program in the next class. I didn't copy that particular program. So we'll move to the presentation. Okay. So already we have seen this. Again, we are having atomic decrement and compare and swap. So in compare and swap, we can use long int and okay. So all those things. So int and send int. Okay. So apart from those functions, we are having the bitwise functions. That is atomic and atomic or atomic XOR. Okay. So atomic AND function. So what it will do is it will take the value in that particular memory location and perform the AND operation, store it there in the same. Okay. It's same for all those things. Okay. So that's all in today's sessions. In today's session, we have seen uh, so some of the memory related concept like so what happens, how to use, how to allocate space for L1 and shared. Okay, what are the function we have to use? After that, how we can allocate memory dynamically, and what about the bank conflicts and all? and two more memory is available, that is textual memory and a constant memory. Both are read-only memory. How we can use those memories. So all these things we have seen. So next is some atomic functions, how we can write uh, CUDA programs using atomic functions. Okay. So known is executing. Okay, that's all today. We'll see you tomorrow. Thank you.
Ma'am, one query.
Yes.
Ma'am, earlier when you executed now that CUDA thread, okay, it was kind of little bit random, like threads, some 17, 16, like that, okay. So in that particular thing, okay, is there any scheduling, how which index will got execute, well, which thread, like that, some kind of scheduling is there, or it will, randomly any thread can be, get executed,
Actually,
or it will run?
yeah, yeah. Actually, what happens is the randomness comes because of the memory access. So, which thread accessed quickly, that will be executed. That is the
Okay,
reason.
so ma'am, okay, so in our that CUDA thread and structure, na, that indexing is starting from 0 0, right? And then it will go from 1 0, from
Yeah.
horizontally, and if you go vertically 0 1 0 1. So which one it will first go? Like it will go to like right hand side, like 1 0 2 0, or it will always go to like 0 1, sorry, 0 0, then 0 1 0 2, like this type of thing. Which block it will
So
first
always
go, sir?
it will go 0 0 1 2 3 likewise only.
Okay.
It will be automatically incremented.
Mhm.
There is no need to increment by in the program. So the thread
Okay.
indexes will be incremented automatically.
Okay.
Okay.
So there is no certain mechanism you will know कि this particular thread will might be executed first, then other thread. Suppose
That
my question is, ma'am,
will
query is like we have
I
thread
understood
one
your
zero, right?
question.
Huh,
I
huh,
understood
sorry.
your question. You asked
Hmm.
how we can know which thread will be executed first and which thread will be
Correct.
executed next, right?
Yeah.
Okay. So actually, the thread execution is based on the data fetching. Okay. So we couldn't identify which one will be executed and which one will be executed next. So otherwise,
Okay.
in initial classes, I told no. So how many blocks, how many threads, whatever maybe you want, give. Okay, while launching the kernel, there is no restriction. Okay, so that will be handled in backend by the CUDA framework.
Okay. Thank you, ma'am.
Thank you.